All right, so we're going to take a look at the last half of Unit 1, Park Practice, 11 through 16. Here we go. All right, so we have a shape. We're going to call that shape 1. And we are going to, as I set the pen here, and we are going to do some sort of transformation such that we end up getting figure 1 to become figure 2. And it's going to take not one, but two different transformations to make this happen. So let's see what our options are, and then we'll eliminate the options as we go. Okay, so a reflection across the x-axis. Now, a reflection across the x-axis is going to create a figure, well, 1, 2, 3, so we have 1, 2, 3, one, 2, 3 spaces above the axis. That would go 1, 2, 3 spaces here. And so we'd end up with a shape that looked an awful lot like this. 1, 2, 3, there we go. Now, I gotta tell you, that looks like it's gonna be a winner. But let's just double check, what are our other options here? So I could then do a rotation that is 180 degrees, and a 180 degree rotation about the origin. Doesn't matter if it's clockwise or not clockwise, it's gonna end up in the same way. So here's a 180 degree rotation. That is clearly not going to help us in this problem unless we could still do a reflection over a line that is x, I have the hiccups, x equals something, but probably not. And then a translation 2 units to the left, well, 2 units to the left is just going to move this object 2 units to the left, and that's really not going to help us. All right, so I'm willing to bet that our first drop-down box is going to be the reflection over the x-axis. So let's see if one of these options will give us the final figure 2. So we have a reflection over the y-axis. Well, if I look at my red shape and I reflect over the y-axis, it's not going to become figure 2. But a rotation 90 degrees clockwise about the origin, well, if I do that, what's going to happen? 90 degrees clockwise about the origin. So if I take this shape and go 90 degrees clockwise about the origin, yeah, that's not going to do it. Nope. But I could do a translation. That's sliding it 3 units to the right. And voila, we got it. So we know that this is the correct combination. All right, so let's take a look at our part 2. So part 2, I'm going to move these shapes back to where they were, maybe. All right, so part 2, we're going to use figure 1 again, and we are going to turn it into figure 3. And we're going to go through the same sort of work we did before. So the first, it has a reflection over the y-axis. So if I reflect 1 over the y-axis, I'm going to get a shape that is at 5, 3. So this corner here corresponds with this corner here. And so we have 3 by 3 by 3, and then this is going to go up 2 more. Here we go. And I can see right now that that's not going to help us really get to this figure right here. So I'm going to just get rid of it. We don't want that. All right. So then our next choice is a 90 degree rotation clockwise about the origin, and then a translation 7 units to the right. That's clearly not going to work. But a 90 degree rotation about the origin, well, that's probably going to help us out here, because I can take this shape 90 degrees clockwise about the origin, and now it's the mirror image of figure 3. Oh, so I'm hoping to do a mirror or a reflection over the x-axis. I hope that's an option, and look, it is. If I do a reflection over the x-axis, I'm going to get figure 3. All right, so that's what we got so far. Let's take a look at the next problem. All right. The graph represents y as a function of x. Place 1 additional point on the coordinate plane so that the graph continues to represent y as a function of x. So remember, a function has to be something on a graph that passes the vertical line test. And if something fails the vertical line test, it's because you have 2 points that are right on top of each other. And that would mean that if you have 2 points on top of each other, when you bring that line over it, you're going to have the line touching 2 points at once. That's no good. So that means I can put the point anywhere that I don't already have a point. So notice how my blue dot is not on top of or below one of my magenta points. So that works. So actually anything along the line of x equals -5 works. Now does that work? No. Because now I have 2 points that are directly below or above each other. Anything along this line will work. No, not that one. But that one. Nothing along this line because we already have this point. Nothing on this line. Nothing along my y-axis. But I could put stuff where x is equal to 1. Likewise, I could do x equals 5 anywhere, or I could put it on this point. I just can't have 2 points that are overlapping. And remember, a function does not have to follow a pattern. I do not need to feel compelled to put this right here just because it looks like it follows the line of best fit. I can put it anywhere I don't already have a point on that x line. All right. I'm going to sneeze, excuse me. Bless me. All right. See ya, Laura. All right. So the next one, rules of exponents, definitely are going to be on this. It's not a huge part of PARCC CMAS, but you know what? It's still something that can be on there. So right now, let's look at the rules of exponents. So the rules of exponents say a to the x times a to the y is equal to the a to the x plus y power. A to the x taken to the y power is equal to, well, this is where we multiply them, x times y. Well, following this pattern, so if we're multiplying the two bases that are the same and we add the exponents, well, what happens if you divide the bases that are the same? So if we have a to the x divided by a to the y, that's going to be equal to the a to the x minus y power. That one might be helpful for this problem because I can see right here I have a fraction. Also, I know, and this is going to be helpful, I see some negative exponents. I know that a to the negative x is going to be equal to 1 over a to the positive x. All right, and then one more that I should throw in there, a to the 0, or anything to the 0 power is 1. So these are rules that we have to know to be able to do this problem. So the first thing I notice is, well, I have a division problem, and when we're dividing, we have to subtract the exponents. So this is going to be equal to 3 to the negative 8 minus negative 4 power. Well, subtracting a negative is like adding a positive, so really this is the same thing as saying 3 to the negative 8 plus 4, which is equal to 3 to the negative 4th. So I can safely click this one right here. But it's a multiple select. There might be another statement that's equivalent. And so let's take a look at this. I see here that I have a negative exponent. So what does it say about negative exponents? Well, it says negative exponents create fractions. Actually, when I create my fraction, my exponent becomes positive. So that means 3 to the negative 4 also is equal to 1 over 3 to the positive 4th, which, oh, look at that. That option is E. So I'm going to go ahead and click E. Maybe. Okay. I feel like I might want those later. I don't know. So I'm going to keep it. All right. Next one. All right. So I'm going to show 2 ways of doing this problem. So we have line S, and line S is going to be at y equals 1/3 x minus 3. Well, what's the y-intercept? The y-intercept is negative 3, so I'm going to put a dot at negative 3. All right, and then I'm going to slide up so I can see my equation. and I have a slope of 1/3. So that is up 1 to the right 3. Up 1, right 3, up 1, right 3. All right. So I'm going to go up 1 to the right 3, and I get my line. Sweet. All right. So then let's switch to line 2. So line 2 has a y-intercept of +5. So I'm going to click +5, and it has a slope of -x. Well, -x, that's just -1 times x. So -1 means down 1, right 1, down 1, right 1. And so I'm going to go down 1, right 1, and there we go. All right, look at that. And so now I have a solution to a system of equations, because you know that a system of equations has a solution where the lines intersect, right? So I'm going to put point P right on 6, -1, because that's where the lines intersect. All right. So let's see. I think I've answered all of the question here. Yep, I have. Now, if you don't have a graph, well, what do you do? Here's what you do. So I can't help but notice that on this graph, at this point right here, y is equal to y, right? The two y values are equal. The whole thing is equal, right? Because it's 1 point. So if I slide up here, I know that y is this whole expression here. And I'll use blue because that's what they used visually. So we have this y. Okay. So we have 1/3 x minus 3. And that's going to equal my red line, which is -x plus 5. All right. Well, using a trick that I saw some of you use today in class, I'm going to multiply this whole thing by 3 so I can get rid of the fraction. 3 times 1/3, well, that's just 1, so we get x, 1x. 3 times -3 is -9. 3 times -x is going to be equal to -3x. 3 times 5 is 15, and that's a +15. Roll that up. All right, so let's go. So add 4x plus 4x. I get 5x, and then minus 9 is equal to 15 plus 9 plus 9. I get, what do I get? Oh my God, why did I add 4x? I'm an idiot. Don't respond to that. I should have been adding 3. Add 3, that gets me 4. Why did I write 4? I'll tell you why I wrote 4. Because 3 plus 1 is 4, and then I was thinking 4, so that's the answer. Okay. So then, so we have 4x. That's just cancels out. And that is equal to 24. So divide by 4, and I get x is equal to 6. No way! This is so cool. That's exactly what we had with this point right here. X is equal to 6. Okay, so well, how do I get y? Well, I could just plug in 6 into one of the two equations. So if I have -6, because that's x, right? -6 plus 5, what do I get? Well, I get -1. So y is equal to -1. All right, so that's a way I could do it without graphing it, which is so much cooler. Although I have to say this is a pretty cool graphing thing, because much better than graphing it by hand, right? All right, show the line of best fit. Okay, so a line of best fit is not necessarily going to touch all of the points, but it goes through the middle of most of them. D is way too high. Most of the dots are below. This just doesn't look right, right? Most of the dots are below the line, and the line is kind of flatter compared to the dots. This looks wrong for the exact opposite reason. It's too steep, and most of the dots are above the line. This is the Goldilocks one. Just right. Not hot, too hot, not too cold. It's just right. All right. And then finally, right, everybody's favorite, scientific notation. So a body of a 154-pound person contains approximately 2 times 10 to the -1 milligrams of gold and 6 times 10 to the 1 milligrams of aluminum. That means we have a lot more aluminum than we have gold. Otherwise, who knows? We'd be melting people down. Based on this information, the number of milligrams of aluminum in the body is how many times the number of milligrams of gold in the body. So, all right, so we're doing a little division here, right? So we have 6 times 10 to the first divided by 2 times 10 to the -1st. And, oh, you know what? I think these rules are coming back. Yeah, we're dividing fractions again, or we're dividing exponents again. So when we're dividing with exponents, we have to subtract the exponents. Okay, so that's going to be helpful for this one. All right, so I'm going to divide this into two problems. 6 divided by 2 is 3. Well, that's easy enough. But here we have 10 to the first divided by 10 to the negative first. So what am I going to do? I'm going to subtract these. So I have 10 to the 1 minus negative 1. 1 minus negative 1 is 2. Not 0, it's 2. So we have 10 to the second. 10 to the second is 100. So times 100. What is 3 times 100? Well, that would be 300. So I know that there's 300 times more aluminum, sorry, for you Brits out there, aluminium, than there is gold in the body.